Okay. Okay, let me read this problem and then you guys we can talk about each of these steps here. So number one says the rate at which the water flows into a tank in gallons per hour is given by a positive continuous function r of time t. The table shows rate at selected values of t for a 12-hour period. So water is coming into a tank, and they're just measuring at these specific hours. So at 0 hour, there's 14.5 gallons coming in per minute per hour, and then 2 hours later, the rate is coming in a little slower, right? So 13.6 gallons per hour. But all this time is accumulating, right? There's more and more water coming in, and it's like imagine you're turning a faucet on either at full blast or at a trickle, right? So these are just kind of variations of it where water is still coming in, and then part A, it says explain the meaning of the integral from 2 to 11 of r of t in terms of the water in the tank. So I think it would have been more helpful if I had used like lowercase r, just to kind of have that distinction. So when you take the antiderivative, you're changing what you're working with. Okay. So this is first theorem, which tells us that if I take the antiderivative, this r is going to turn into an uppercase R. And it's going to become R of 11 minus R of 2. Okay. So now I think a lot of us are struggling in terms of, we know it's some sort of an accumulation, but your units is going to change as well. Okay. Instead of gallons per hour, do you know what this is going to turn into? Okay. So I think we understand what happens with derivative, right? So derivative, we know that gallons per hour would turn into gallons per hour per hour. But when you take the antiderivative, you end up losing a rate. So instead of gallons per hour, this is going to turn into total gallons. Okay. So R of 11 is going to be measuring how much water is in the tank in the 11th hour. And then R of 2 is how much water is in the tank in the second hour. And then the difference between 2 and 11 is how much water has been added in that time period. Oops, second and 11th hour. In terms of gallons. Okay. Approximate, does that make sense?
Yes, it does.
Okay. So anytime you take the antiderivative, you have to think in terms of, all right, my units has got to change. All right. So whatever your units is, you're gonna lose that one of the rates. Okay. It's like velocity, right? If you take the antiderivative velocity, your feet per second or miles per hour is going to turn in terms of miles. So you're losing a rate when you take the antiderivative. Okay, approximate using trapezoids. I think you guys are pretty good here. I didn't see any issues here, but trapezoids, you find an area. So from 2 to 11, width over 2. And then width over 2. and whatever that number is. Okay, so this is going to tell us roughly how much water were added in that time period. And then using approximation from part B, find the average rate of water change, water flowing. So this is using average value theorem. So it's 1 over B minus A, integral from 2 to 11 of R of T. And then so we just take this 1 over 9, right, whatever all this value is, so what happens is that we know that this is in terms of gallons. But then you're turning around and you're dividing by the time again, by hour again. So when you take the average value theorem, you change your units to gallons, but then you're turning around and you're dividing by time, so you're back to gallons per hour. Okay. All right, number 2 is a lot of just calculator work. So what calculator do you guys have? Do you have a 36 Pro or do you have 84?
I have 36 Pro.
Okay, yeah, 36 works. So what we want to do is we want to find the x-intercept. So to find the x-intercept, we have to first figure out where the graph is. So we go to the table, edit function, type in the function here. Make sure that you're in radian mode. So go to mode, make sure you're in radian mode. Okay, so e to the square root of make sure you get out of the square root and then scroll over and say minus sine x. Okay, minus 5. Okay, we're going to start at 0, but we're going to increment by smaller steps. Okay, so we want our table values to not give us whole numbers because we may miss. So maybe do like 0.5. So you can ask the calculator to give you order pairs every increments of 0.5, and then we're going to be looking to see when our when the velocity is going to change signs. Okay, just to kind of give us some idea. So, all right, so we see these are negative velocities here. Looks like it's moving towards a positive value right around here. Okay, so we know somewhere between 3 and 3.5. Right, we can gain more accuracy later, but right now there's at least 1, and that may be it. Right, maybe just see that there's that 1 sign change. Looks like past 5, it's we don't care about anything past. Oh, actually, yeah, past 6, we're not going to care about it. Okay, does that make sense so far? Okay. Now we want to gain more accuracy. We know somewhere between 3 and 3.5, the sign is going to change, but there's be some, we want a better value. So go back to table, edit function, and now make your step a little smaller. Let's say 0.1. We know somewhere between 3 and 3.5, so you can start at 3 and start looking for it. So between 3 and, looks like between 3 and 3.1, right? Looks like that's where the sign is going to change. And then we can gain even more accuracy. by going to step by 0.05. Oops. Even smaller intervals. Yeah, so that's pretty good. We'll say like 3.04 or 3.0. Yeah, 3.04 looks like that would be a pretty good one. Okay, I guess we go a little further here. Increments of 0.01. That's probably as good as it's going to get there. Okay, 3.0. There we go, 3.01. Somewhere between 3.01 and 3.02. Because velocity change signs. Find his acceleration. So acceleration means we got to find the derivative. So you're going to go back to your home screen. So second mode. And we're going to go to derivative feature. So d over dx. And then type in the function which we can call from the table. So if you go to table 1, x, f of x, make sure you close the parentheses though. And we want to ask the calculator to evaluate the derivative at 3. So acceleration our units is inches per second squared. Okay. Bree, how are you coming along?
I'm actually following it really well.
Okay.
I was confused about the calculator part, so this really helps.
Okay, good. Yeah. So, yes. Let me know if you want me to slow down or if you have any questions. Okay, part C, it says, is Pierre's velocity increasing or decreasing? I think a lot of students get confused between velocity and speed. So if I ask you for speed increasing, decreasing, then you got to compare signs between velocity and acceleration. Okay, so let's say it was speed increasing. Speed increasing, that means you got to find velocity at 3 as well. That's not part of this problem, but we do need to. So if you want to find velocity at 3, what you can do is you can go to table F. So right now our function is at the velocity level. Plug 3 and negative 0.09 inches per second. So here's acceleration, here's velocity. If it says whether speed is increasing or decreasing, we compare the signs. Same signs, increasing speed, opposite signs, decreasing speed. So this would indicate decreasing speed. All right, but it's asking for velocity increasing or decreasing. Careful, because this is not asking about velocity. It's describing it's a rate of change of velocity. So because of that, it's actually just asking about acceleration. So because acceleration is positive, my velocity is increasing. If acceleration is negative, then we'll say velocity is decreasing. Okay, so that one little word and these two descriptions is affecting how we interpret it. Okay, good so far? Okay, so we say velocity increasing because acceleration is positive. Find a total distance. So total distance is different from displacement. So displacement is just going to be the integral from 0 to 5 of the velocity function. Again, go to table, f of x, close parentheses. Okay, so displacement is the net gain. We don't take into account whether it's moving forwards or backwards. We just want to know how far is he from his starting point. Okay, it may take a while. Okay, 11.47. That's the displacement. Okay, so that's not distance. Displacement is 11.474, but it's asking for total distance. So total distance, displacement is just from 0 to 5 of velocity dt. Okay, but if it's asking for distance, then it's the integral from 0 to 5, absolute value of v of t. And the difference is that we got to put absolute value bars around f of x, or around the velocity function. So again, go to your integral notation, second integral from 0 to 5. Absolute value. So to get to absolute value, you're going to go to math, number, ABS. Math, number, ABS. Type in your function, x, close parentheses. And this will take a while. It may take like 30 seconds. It takes a little bit longer for this to process the absolute value. Okay. Hey, Evan, you have any questions?
Not right now. I think you've covered most of mine already.
Okay. Hey, Bree, all these keystrokes make sense?
Yeah, they do.
Okay. All right, let's go to next page. Find the derivative of this. So we have to understand that there are two opposite processes going on. There's the antiderivative and there's a derivative. Okay. We're going to find the derivative of this antiderivative of this function. So if we're pairing two opposite process on top of the function, we know that this is not going to change a whole lot, right? It's like, imagine you're adding something and then you're taking it away. Right? If you're adding something and taking it away, you're kind of back to where you started. So we are applying two opposite process on the function. So there's a bit of a shortcut that we can do. So we're not going to take the antiderivative and turning around and find the derivative, because if we're going to end up where we started, we can just put that down. But this variable is going to have some impact after everything's said and done. So this is a bit of a shortcut called the second fundamental theorem of calculus. And all that says is that if I want to find the derivative of an integral of a function, I just have to keep track of how this is impacting this function. So this function is not going to change, but this variable is going to get inserted into the function, and the derivative is going to have an impact there. So these two processes does have an impact of that variable in this function. So the end result, we're just kind of jumping to the end. We're not going to do a whole lot of process, because we're going to largely, this function is not going to change much. But this variable will get plugged into the function. So we say f of p of x. So everywhere we see a variable here, it's going to be inserted with this expression. Multiplied, the derivative is going to have an impact on this variable. So it's going to look like this. Okay. So if we apply it to this problem here, d over dx, integral from 5 to root x, 1 minus t. Okay, so what do you think? What would this look like if I were to plug the upper bound into the function? Okay, Bree or Evan?
Do you mean the px?
That's right. Yeah. So this p of x is the root x. So what would this look like if I put the root x in for all the t's?
Would it bring up the denominators up high?
Oh, you mean the 5? Yeah, the 5 is not going to have impact. The 5 is going to just go away. So we're just going to insert this variable into the t. So what would that look like? Okay, I'll do the top part here. 1 minus root x. Okay, what's the bottom going to be?
Would it be either 2 plus square root of x with the exponent of 3, or would it be 2 plus x square root 1/3?
What you said first. Yeah.
Okay.
We're just going to insert this entire thing in for the t.
Okay.
So 2 plus root x cubed. So what you did here is you're following the rule that is telling you here. So notice that we didn't change this whole lot, right? We didn't do the derivative, we didn't take the antiderivative. All we did is we just plugged in, because we have two opposite things that are impacting the same function. Times, what's p prime going to be? Or how do we find p prime? Okay, p prime means find the derivative of square root of x. So how would you find the derivative of square root of x? Okay, we'll get it ready for power rule, right? So square root of x is the same thing as x to the 1/2. So what's the derivative of x to the 1/2? Okay, here's power rule. Bring down the exponent and subtract 1 from the exponent. So what's the root of x to the 1/2? What do you guys think?
Is it 1/2 x to the negative 1/2?
Yeah. Breeze, that makes sense?
Yeah,
Oh.
so you subtract 1 to find the derivative.
Right. Yeah. Yeah, it's like 2x cubed, right? 2x cubed. We bring down the exponent, subtract 1. We just have to deal with a fraction here. Yeah, and that's basically it. Just follow the rule that says. Guess we can clean this up a little bit. All right, number 4. Given that the region between 3 and 6 equals -2, and the region from -6 to 0 equals 9, find the region from -6 to 3. So this is our ultimate goal here, trying to find that region if function is odd. Okay, so the first step is we're going to sketch the shorter interval region. So 3 to 6, -6 to 0, we want to pick the shorter region. So we're going to sketch the shorter interval region. So from 3 to 6, it'll be -2. So let's say this is 3, this is 6. And we know that there's going to be symmetry kind of on both sides. So for odd functions, okay, from 3 to 6 is -2. So that means we want to create a region below the x-axis with an area of 2. Okay, that's what that negative means. So here's a region we'll call -2. Okay. Now, as soon as you sketch your shorter interval region, you want to create that behavior on the other side. So create either even or odd behavior of the region. So if this is an odd function, do you know what happens to this -2? Or how is this displayed on this side? Any idea? If it's an odd function.
It becomes positive.
That's right. That's right. But if it's what if it was even?
Then it would stay in negative.
Good. So either if it's even, you're going to create a mirror image. If it's odd, you're going to create equal but opposite. So this is odd, so this is 2. Okay. Now, these regions are set in stone. Okay, we're not going to make any changes here, so there's no overlapping of anything. Okay, no overlapping of this region. Now we can move on to our other region. From -6 to 0 is going to be 9. So we know that we want this region here to total to be 9. So if we want this region to be total to be 9, this is already set as 2. So what must be this missing region?
7.
Yeah. Right. And if this is 7, then this must be
-7.
There we go. And then we just add what they're asking us to add from -6 to 3. So we're looking at the 2, we're looking at the 7, we're looking at the -7. All that totals to be just 2. Okay. Now this is what it would look like if it was an even function. If it was even function, let's say we're looking at the same problem, we're just changing it to be an even. We're still going to start off with -2. But like you said, Bree, it was going to be even here as well, -2. But we want this to total to be 9. So what is this region going to be if it's even? I'm sorry, yeah, what would this region be in order to make this a true statement?
-7.
So if I put -7 here, what's -2 minus 7? -9, right? So
Yeah.
I gotta have a larger positive number to balance out that -2. So what
Would it be
positive
11?
number? Say it again.
11.
That's right. Yeah, 11. So 11 minus 2 equals 9. So this 11, what do we put on this side if it's even?
11.
Yeah, mirror image. And if it's asking for your total from -6 to 3, we're just going to add this up. So that's 22 minus 2, which is 20. All right, let's look at number 6. Evaluate the integral 6x square root of fifth root of 2 minus x. The first thing we have to understand is we can't distribute this, right? This is stuck inside. We can't distribute this through order of operations. We're kind of stuck. So let's rewrite the problem, though. Maybe this is a U substitution problem. So how can I rewrite this? This is parentheses to what power?
Or 1/5 power.
1/5, right? Okay. We can't distribute. It's got to be a U substitution problem. So what's our U value? Any idea?
Uh, 2 minus x.
Yeah, I consider this a kind of like an easier problem to find the U value, because if you can create a set of parentheses, whatever's inside your parentheses is usually a good place to look for the U value. Okay, we're going to underline these two parts because these are the first two things we're going to try to replace. We're trying to get all this in terms of U, and hopefully we can find an integral rule we can use. Okay. So we'll let U equals 2 minus x. D over dx, we got to find the derivative. So 2 goes to 0, negative x becomes -1. Cross multiply. Solve for dx. Okay. Good so far? Okay, Bree, any questions?
No, not right now.
Okay, so now we're going to make our substitutions, right? So this we can replace with u. Dx will replace with -1 du. And let's see where we're at. We want to convert everything to be in terms of u. We're making some progress, but what's not going away by itself?
The 6x.
That x is not going away. Okay. Now let me tell you what a lot of students want to do. They see this, and a lot of students want to continue. Be like, all right, this is power rule, that's power rule, so I'm going to make this 6x squared over 2, and then I'll make this u to the 6/5 over 6/5, and then I'll put a plus c. We can't do that. Okay, that multiplication prevents us from being able to move forward. We have to get everything in terms of u before we can do our calculus step. Right, so we can't just jump into power rule for both these terms, not with multiplication and not with two separate variables. So we have to find a way to get this x to be replaced. Do you see a way that we can get that x to be replaced so that everything that we're seeing can be just one variable in terms of u? Okay, so here's the hints. The hint is over here, this u equals 2 minus x. Do you see anything that we can do here to get that x to be replaced? What do you guys think?
We can just make x in terms of u.
Yeah, so let's just rearrange this equation, right? What if I can solve for x? If I add x to the left side and subtract y from the other side, can I not make this x equal to 2 minus u? Right, just kind of rearranging something. And now I can replace x in terms of u because this can cleanly substitute in for that x. So look to see what we have now. 6 parentheses 2 minus u, u to the 1/5 times -1 du. So we're still not out of the woods yet, but at least we've gotten all of the variables to be connected, right? We got rid of that x. All right. Evan, Breeze, that makes sense so far?
Yes, it does.
Okay.
Yeah.
So we're not out of the woods because we still got to expand all this out. Okay. We still can't do power rule, power rule. We got to get all the parentheses resolved. So I'm going to rearrange. I'm going to put the negative in front with the 6. And I'll bring the -1, the u, and the 6 all together. That way I can just get a single term and distribute it through the parentheses. Okay, distribute this through, multiply. I'm going to be adding exponents though when I get to the u. One-fifth plus 1 is going to be 6/5. And now we can apply power rule. Okay, everything is nice and clean. Everything's separated. No parentheses. No ugly exponent, or I mean, no exponent in terms of a parentheses. So we can jump into power rule. So power rule is this. Okay, we add 1 to the exponent and divide it by that new exponent. So I'm just adding 1 to the exponent, which is the same thing as I add 5/5 for this one. I'm adding 5/5 for this one. Okay, we're almost there. We're just going to clean this up. We're going to flip the fractions to be reciprocal so it can comes back up, and we can replace u back in terms of x. So this becomes -2 times 5, so it's -10 u to the 6/5 plus 30 over 11 u to the 11/5 plus c. And don't forget, we started in terms of x. We're going to end in terms of x as well. All right, number 6. Okay, how are you guys coming along? Does that make sense?
Yeah, it makes sense.
Okay.
Yeah, it does.
Good. Number 6, we see bounds, but we know to start our problem, we ignore the bounds and rewrite the problem. The bounds is the last thing we do. So just like before, we see we can't distribute, we got to do u substitution. So same thing as this, but it's going to be a little cleaner than what we experienced with number 5. But we're trying to get everything in terms of u. The nice thing is that this is x squared, so this should, after the derivative, should handle this x a little bit more cleanly than it did for number 5. Okay, cross multiply, solve for dx. I'm going to replace what I underlined. All right, what do you guys see here? What is nice and clean about this problem that we couldn't do with the last problem? what can we do with the x's? Okay. One's in the numerator, the other's in the denominator, so guess what we can do?
Cancel them out.
Yeah, that's right. Before we couldn't do that, right? Before we're kind of stuck. There's no x's from our derivative that will take out that x, but now we have something. So that's a good sign. Usually if your u value is a degree that is higher, 1 degree higher than the x that you're leaving alone, that's a good sign because we know that down the road it should match up and reduce for us. Okay, so we'll pull the x's out, remove them, and then we can push that 2 out in front to make it a little cleaner. So now we have a nice, clean power rule problem. Much easier than before. Okay. Go directly into power rule. Clean this up, flip that 2/3 in front, so it becomes 1/3. Get the 2's to cancel out, and then replace the u back in terms of x. And once everything's in terms of x, you can now cleanly use the bounds. Now I can involve those bounds. Okay, do you know which number gets plugged in first? The 4 or the 0? What do you think? Okay, Bree, what do you think?
Would it be 4?
Yeah, upper bound gets evaluated first, always the top number. Even if this is out of order, we always, if it's out of order, we leave it alone. Okay, we're not going to, the process is going to end up being the same. So always plug the upper number first. And this is going to be some number you can plug in the calculator, or you can leave it alone. Okay. Okay. I didn't get to finish all the problems, but does that help so far?
Yes.
Yeah, it does.
So I'll have another help session this afternoon. And if you can't make it, then you can watch the recording. I will finish these problems first, and then I'll go back to the previous ones for students who are joining for the first time. Okay, and then that will help. Hopefully, that'll help you with your test corrections.
Where are you going to post the recording of the other help session? Because I won't be.
Yeah, I'll put it in the help session channel, but if I have time, I can maybe put it under on my website.
Okay.
Okay. All right. See you guys.
Thank you.
Okay. Bye.
Bye. Thank you.
Bye. Mm-hmm.